Hello and welcome to another video. In this video we're going to be continuing on with the TypeScript Blind 75 and we're going to be doing graph valid tree. So in this problem you're given a graph of n nodes labeled 0 to n minus 1 and a list of edges a, b where there's an undirected edge between a and b for every edge, and you want to return true if the edges of the graph make up a valid tree and false otherwise. So like in this example this is a valid tree, and in this example this is not a valid tree. So the first thing we're going to want to write down is what is a valid tree, and that's going to be the important thing to know. So valid tree rules. A, no cycles, just like here, right? No cycle. If there's a cycle, it's not a valid tree. B, every node is connected to every other node. And C, if you actually notice, for a valid tree, in order to make it no cycles, the number of edges equals n minus 1. So if you look here, we have 5 nodes and 4 edges, and here we have something that's wrong. So any tree, we can just draw like some tree. Let's say like draw this tree, 3 nodes, 2 edges. You know, this can have a bunch of children. And that's essentially because, if you think about it, every single node has an edge up to its parent, right? So every node has an edge up to its parent, except the root doesn't have one. So every node has an edge going up, except the root, so that's n minus 1 edges. So for a valid tree, we have to have this. And so these are kind of the rules we need to have. So every node is connected. And so notice we're checking for connections. So I'm actually going to do this using union find. There's like a bunch of ways to do this, but I think using union find is kind of cool. And I think union find is the one algorithm I would recommend memorizing pretty much. Out of like every LeetCode algorithm ever, because it's decently long and it's very useful, and I think if you don't memorize it, it's hard to come up with it on your own. So I definitely recommend just doing enough union find problems, writing it out until you can kind of memorize it, and I've done enough to where if I had to code it up, I could. And so that's what we're going to be using. So we're going to be using union find. So let's briefly describe union find. So union find is essentially an algorithm that's used to check if nodes are connected, right? So we have union find takes some n number, and it checks if all these nodes are connected. So it takes n nodes and checks for any 2 nodes. Are they connected? And it can also connect them. So union find has a few functions, right? It has a find, which gives you the parent of a node. It has a union, which connects 2 nodes by using find, right? So it'll check for the parent, and if they have the same parent, it will also, you can also like make it return things. So it essentially connects 2 nodes. You can also use it to tell you if they are connected. So I think the original one on LeetCode might not tell you this, but it's pretty easy to do. So essentially you can have in your union logic, you can just say like, if they have the same parent, let's just return false. Otherwise, let's connect them and return true. And so if there is this other function, which you don't necessarily need to have, you can just put the logic into union. So there's like an is connected, which just tells you if 2 nodes are connected. And the way like you connect nodes and you check if 2 nodes are connected is you use find to get the parent of a node, and then once you get the parent, you just check like if they have the same parent, then that means they are connected already. So essentially has these things. So I did just write the code in TypeScript preemptively because I don't want to like be coding up the union find as we go. But this is the one, and I'm going to also link like the LeetCode Explorer card with the union find code. But this is the one LeetCode thing that I would recommend memorizing. I think it's quite useful. And in a lot of problems, it's like the best and cleanest way to do things. So essentially, this is what we can have, though. So let's say we have like nodes 2 and 0. We can simply call union on those nodes, and they will either get connected, or we can know like they are connected already. So now how can we use union find to tell if we have the tree, right? So let's just draw up some random tree. Let's say we have a tree like this, some nodes. And like, how do we know if this is a valid tree, right? So one thing we can check is, well, we're going to have a length of edges, right? So remember, our length of edges, if it's not equal to n, so let's say here we have 5 edges and 6 nodes. So if the length of edges, let's call that e, does not equal n minus 1, right, does not equal n minus 1, we can just return false right away, because for a valid tree, the list of edges has to be n minus 1, just like we described earlier, right? Every node has one edge coming up, except for this parent. Now, this might not necessarily mean that the tree is connected, because you can still have the right amount of edges, but your tree can still be screwed up, and let's just go through an example here. So let's say we have something like this. So here we have 1, 2, 3, 4, 5 edges, but this is not a tree, right? This is not connected to anything, and this has a cycle. But essentially, for a tree, we're just going to be looking for cycles. So we need to figure out, like, how do we efficiently detect cycles, and how do we efficiently make sure our edges are connected? And so this part is going to be pretty straightforward. So let's start off with, let's actually go back here. So let's say we have our list of edges, and let's draw some nodes. So let's say this is 0, 1, 2, 3, 4, 5. And let's say our list of edges, just to make it easy, is just going to be like in order, right? So 0, 1, 0, 2, 2, 3, 2, 4, and I'll draw the last one down here, 2, 5. So essentially for every edge, so if you actually drew out all these edges, this would make a valid tree, and then we'll do one that's not valid. So essentially every edge does connect things, and so for every single edge, you can just call union on your two nodes, and essentially union will connect them, so we'll represent that with a line. And then every time a union is successful, we can decrement from n, or whatever, we can keep some count of like connected. So what we're going to say first is, originally without the edges, we can just count connected components, right? So in the beginning, we have 6 nodes, so six different components, right? And a component just means it's a part of a graph that's not connected to anything else. So we have 6 components that aren't connected. So we're going to say like some number, let's call this result or something. We'll set it equal to 6. And then we're going to go edge by edge. So for 0, 1, we are going to connect these two nodes, calling union. So we're going to call union on 0 and 1, which will basically connect them. And it will return true, meaning this was able to be connected. So we're going to go through this node, connect this. Let's actually maybe draw some another. It's fine. So we're going to connect these. And now that every component we successfully connect, now our number of components reduces, right? Because if we connected 2 components, they become 1 component. So now this becomes 5. Now we go 0, 2, we try to union them. They're not connected as it is, because as you can see, this is essentially what union find does is if the components weren't connected, it will connect them, but if they were together already, then it won't. So let's say I had this, like let's say I connected 0, 1, and then I connected 1, 2, and then I tried to connect 0, 2, this union would fail, because in union find it would say, no, you can't connect these because they are already connected in one component. So that's how union find works. So it's really good for cycle detection, right? Because if it lets you connect, there is no cycle. And if it doesn't let you connect, that connection will make a cycle. Okay, so yeah, so 0, 2, we are able to connect because they are in different components. Then we'll subtract 1 from result, right? We just got rid of a component. Now we have 2, 3. They are in different components, so we can connect them. Now we will reduce this to 3. Now for 2, 4, they are in different components, so we can connect them. So we'll reduce this to 2. And for 2, 5, they are in different components, so we can connect those. Now I'll reduce it to 1. And now that we're done with our edges, essentially what has to happen is, so assuming we checked for this, assuming this is true, then we don't really have to have a check at the end. But if you didn't check for this, then you would just say like, okay, well, how many components do you have left? I think if you check for this in the beginning, if edges is n minus 1, and all your connections are able to be made, you're guaranteed to get result equals 1, right? Because if it starts at n and you subtract e, you will get 1 because n is e plus 1. So you don't have to check for that at the end. But essentially, if you are able to go through all of your edges, each edge should be able to have a successful union, because in a tree, every edge makes a successful connection and there are no cycles. So this should work. Now let's draw a tree with a cycle, and then we can kind of like do this again. So let's say we have this again. We have 0, 1, 2, 3, 4, 5. we're going to have 5 edges again, just so like our initial thing doesn't fail. So let's have 5 edges. So we'll have 0, 1, 0, 2. Now let's just make some weird edges. So we'll have like 3, 4 is an edge. And then let's have, what else can we have here? So we can have like 2, 3 is an edge. And now let's just have like 4, 0 or something, right? So we have a cycle. So let's kind of walk through what this would look like. So we're going to start with the result. So actually, I don't even think you need a result, because if you do the check, yeah, I don't think you need the result, because assuming you already checked that edges is n-1, if you just went through all your edges and all your unions are successful, you're always going to be able to return true. And if you ever have an unsuccessful union, then you can just return false. So let's kind of walk through this one. So we do have 5 edges and 6 nodes, so that part is fine. But let's walk through if this is actually possible. So for 0, 1, they are not connected, so we can connect them. We can return true there. For 0 and 2, they are not connected, so we can connect them. For 3 and 4, not connected, fine. For 2 and 3, not connected, fine. So you could see like this tree, even though it's kind of weird, would still be valid. Like let's say like I just had 1 connected to 5. Like that's actually a valid tree, right? I mean, I would have to draw this a little bit differently, but this is a valid tree. But the problem here is that, so 2, 3, it does work, but then when we try to connect 4 and 0, we're going to get an error here. This union would return false because they are already connected, right? They are already in the same component. So you can't connect 2 nodes in the same component with union find. There would be a cycle, so we would just automatically detect it and we would just return false. So essentially, you go through every edge, and first you make a union find data structure, which I'll talk about in the code. Then you go through every edge and you try to connect the nodes in it. And they should be allowed to be connected if you have a valid tree. If any connection ever fails, then you just return false. And because we already checked that the number of edges is n-1, that'll save us time as well, right? Like in a valid tree, that has to be the case, so we might as well check for that beforehand. And then if all our connections were true, that means there shouldn't be, I'm pretty sure, any unconnected. Like it's impossible to connect everything, not have a cycle, and have a node that's not connected if edges equals n-1. I don't think it's possible, right? Like once you have this, how do you not have a cycle? You can't. Okay, so let's look at the code now, and then we will code up the actual part that's not the union find. So here it is. So we have a union find, and the union find has 2 things. It has a number array of roots and ranks, and essentially every node is its own parent, and ranks is used to represent the length of the path with the node, right? So in the beginning, the roots all start being themselves, and then the ranks, every node has rank 1 because it's its own parent, essentially. Then we have find, which is a recursive function. So if a node's root is itself, we can return it. Otherwise, we say, okay, let's take whatever the parent of that node's root is, and then let's set it equal to that. And the reason for that is something like this. I can actually draw that one really quick. So let's say we have something that looks like this in our data structure. Obviously, it's an array, but let's say it's something like this. So here's the parent. And so let's say this is node 0. Actually, let's redraw this a little bit so we can. Okay, there we go. So let's say these are our nodes. So let's say this is node 0, node 1, node 2, node 3, just to make it easy. So the parent of node 3 is node 2, the parent of node 2 is node 1, the parent of node 1 is 0, and then the parent of 0 is 0. There is no parent like above it, right? So what's going to happen is when we call find the parent for 3, we're going to say, let's find the parent of 2, and then whatever the parent of 2 of that, let's set it to 3. Then so let's kind of like walk through this. So we're going to say, okay, the parent of 3 is 2. So let's find the parent of 2 and then set the parent of 3 to whatever the parent of 2 is. So we're going to recurse into here. Then we're going to do the same thing for 2. We're going to say, okay, the parent of 2 is 1. So let's get the parent of 1 and let's set the parent of 2 equal to that. So we're going to recurse into here. Now we are going to recurse into here. And finally, the parent of this node is 0. So we are going to return 0 here, and we're going to say, let's make the parent of 1 0. And that already is, so that part is fine. Then we're going to say, okay, now let's make the parent of 2 0. So essentially what we're doing here, instead of making the parent of 2 1, we're going to say, let's make the parent of 2 0. So we're going to, this is by representing these as lines, it's going to look something like this. And then similarly, the parent of 2 0, so let's make the parent of 3 0. So what this does is, if I want to get the parent, these paths are a lot shorter, right? We used to have like a 4-node path to get the parent of 3, and if you keep adding on and adding on and adding on, this gets really long. But now we're using this recursive function, we save a lot of time, because now that we actually reset our tree, we reset our parents. Now all of these parents are like 1 node up. So that's kind of like what the union find with path compression does, is anytime you find parents, it optimizes the paths to make them shorter. So let's go back to the code. And this is what this does. Essentially, you're just saying if the node's parent is not itself, let's just say the node's parent is the parent of that node's parent. So every time you call find, you will essentially optimize the path. So now to quickly go over the union, what's going to happen in the union here is we're going to get the parent of 2 nodes. And if they have the same parent, that top level parent, that means they are already connected. So we can just return false. Otherwise, we get the path length. So ranks represents like the path length of the parent all the way down, like what's the longest path, meaning like, kind of showed that in the picture as well. So let's say we get the parent of 2 nodes. Let's say one node has a path like this, and another node has a path like this. So this is X and this is Y. So this path length is 4, right? Like the rank just represents like what's the longest path. And then, so the path here is 4, the path here is 3. We want to connect these. We want to connect these at the top level, but we want to figure out like how to connect them efficiently. And so if one is longer, essentially what we are going to do is we're going to connect the shorter one to the longer one. So for example, here, Y is shorter. So we're going to say, let's just make the parent of Y X. Because now if we look at the ranks here, the rank of X will still be 4, right? Where if you did it the other way, right? Like if X is the top level here, where if you did it the other way, where Y is the top level parent and you connect X like this, now the rank of Y would be 5, because you would go 1, 2, 3, 4, 5, right? You go down 5 nodes. Actually, I think it depends like how you calculate the rank. I forgot if you include the node itself. So this might be like 3 and 2, but either way, I think it is actually 4 and 3, because it starts off as 1, where every node is its own parent. So I think the path does include the node. But essentially, you want to append the shorter parent to the longer parent, because then you keep the longest path from that parent the same. So it's like an optimized append, essentially. Not super, honestly, like, if you just memorize this and know roughly what's going on, that's good enough, and like know when to use it. You're never going to get grilled on like explain exactly how every single part of union find works. You know, I'd probably just say like watch it. I think honestly the last time I looked at how to like the under the hood union find stuff was like a year and a half ago or something. So I know roughly what it does, but not like everything exactly. And so the main thing is just memorize it and learn roughly what every single method does and the use case for it. So essentially, and now there's one other case where if there's a tie, so if there's a tie, it doesn't matter which one you make the parent, because you're going to make the path length longer for either one, right? Like if they have a path length of 4 and 4, you're going to add 1 to the other, and then one path length will become 5. So that's why we increment the rank of the one that we add the node to. Okay, and now we can use these to actually go through and do our graph valid tree. So let's get some more space here. Okay. So essentially, what's going to happen here is what we need to do is we need to make this union find data structure, right? So we can just say constant union find equals new union find. And so remember, union find takes the number of nodes. So the number of nodes is going to be n. And now essentially what we can do, so right away, like I said, if edges, or if n minus 1 does not equal length of edges, we can just return false, because remember that has to be true. And looks like I'm doing too much Python, so edges.length. So there we go. So if this isn't true, we can return right away. So we're going to loop through all the edges, and they all have to be valid for this to work now. So let's do that. So we're going to say for loop through it, so let I equal 0, I is less than edges.length plus. You could also do like a for of or whatever. It doesn't matter how you do this one. So essentially now you have to try to union everything here, right? So we're going to say if uf.union, and then we're going to give it our 2 edges. So this is going to be edges I 0 and edges I1. So if these work, then we're good. But if not, right? So if this is false, I mean, we can just write it, I guess. So if this is false, then we can just return false because we had an unsuccessful union. So we can return false here. Otherwise, we just keep going and we keep trying to union. So every single edge has to make a successful union. And if we did make it through this for loop and we don't have any issues, we can return true as a default, because I believe once we did this case, we don't have to check for the number of connected components. It should just work. But let's see if I'm wrong about that. Oh. Looks like, let's find out. Okay, so it does work. Yeah, so this optimization is better than checking for at the end, right? Because let's say we have like a million edges and then whatever, a million minus 2 or a million plus 2 nodes, I guess. This can't be a valid tree. So this is better to check for ahead of time. That way you don't have to check at the end, and this is a lot faster in a lot of test cases. So now we have a pretty efficient function. Like I said, for this union find, I'm going to provide this code in TypeScript, and I'll also link the Explorer card with union find. I would recommend practice writing it down a few times, really kind of understand roughly what it does. I don't think it's super complicated. And definitely I would recommend to memorize it, because it's kind of hard to come up with, like on your own if you, or I wouldn't, maybe not even memorize it, but like roughly know what you have to do, and then you can come up with it on the fly, right? I don't like memorize it, but I roughly know what it looks like, and then I can come up with it on the fly. And then usually when I do these, like 1 out of every 2 or 3 times I get a union find problem, I just type it out from scratch. And then the other times I just copy paste from another problem, because I don't want to write like whatever lines of code it is, 40 lines of code over and over and over. So, but I would say definitely a good one to know, and it's very useful for a lot of these connected component problems. You could solve this problem in other ways, but you are going to get other problems where union find is just makes the problem super easy. Honestly, I think the solution is super easy once you get the union find down, right? So, yeah. Let's go through the time and space, and we'll talk about like union find time and space. So for our number of nodes, essentially we made an array, right, of length n, or you can do it this way, or you can just make it. Either way is fine. So essentially this is going to be of length nodes. And actually what you can argue here, and that would be totally fine, is I think time would be O of n here, because you don't have to incorporate edges. And the reason you don't have to incorporate edges is because whenever edges is too different from n, right, edges has to be n minus 1. So if edges isn't n minus 1, it would always just fail, right? Like, so if n is 2 and edges is a million, it would just fail straight away. So because edges has to be n minus 1, this would just be O of n time. Like, it only relies on nodes, not edges, now that we did this beforehand. And I think that would be pretty reasonable to argue. So yeah, so we need n because we need to actually go through the edges, which have to be length n. Or you could argue it the other way, right? You can argue it's O of n or O of e. I think those would both be acceptable. So I guess now that I'm thinking about it, so I think as far as like min O of e, I mean, it would be O of 1 whenever edges are not equal to, yeah, it would be kind of tough to say, because like, let's say n is a million, and then edges is like 2, then this is obviously not going to be O of n, this is going to be O of 1. So I would say, like, I'd probably say, like, I don't even know what you would write for the time there, right? Like, what's worst case? Because it will only work when they are basically equal. So I would even say it's like O of 1, or, I mean, it wouldn't be like O of 1, but it would be like, I don't know, min, maybe you can argue. I'm honestly not sure what you would write there. Something like this, but it would be even faster if they weren't equal, right? So kind of open to interpretation there, but I would still argue that it only relies on one of them, because they have to be the same pretty much for it to work. Yeah, and then this for loop is going to be O of whatever they are. And then, so by the way, these union and find and stuff operations are roughly O of 1. They're not exactly O of 1, but I think for time complexity, you can think of them as O of 1. I think it's like 1 point something, so roughly O of 1. So like every union will be O of 1, every find will be O of 1, and so on. Like I said, not exactly, right? Because paths will be not always one node, but because you are optimizing at every step, they will be roughly that. Okay, and for the space, so we did, like, let's see what we have. So for this union find, we did have an array of length n, right? So yeah, where we have an array of ranks and roots, they're both length n. I don't think we have anything else. I mean, obviously we made this union find data structure, but the union find data structure just has those two arrays. So I think space, once again, kind of arguable. I'll say this. Maybe you could say O of n, you know, of edges, whatever. Like they both have to be the same. Like, yeah, if it's like 2 in a million, then it's O of 1. So I'm honestly not sure what would be like the notation for that kind of stuff. Kind of weird. But yeah, I think that's going to be all for this problem. So definitely, like I said, learning union find is useful. Definitely would be like down the road of algorithms you need to learn. So first learn common graph traversal, you know, DFS, BFS. But then definitely once you're doing graphs, I think union find is a must after those, after common graph traversal. So definitely recommend that. And I think that's it. So if you like this video, please like it, and I'll see you in the next one. And thanks for watching.